Hi students, and welcome to chapter 5 on the arrangements of electrons and atoms. In chapter 4 we talked about neutrons and protons and where they belonged and how to count them up and isotopes. But in chapter 5 we're going to be looking at how are the electrons set up inside of an atom. What you saw in the video that you watched from Crash Course was some information about light. Light, as you learned, is one portion of the electromagnetic spectrum, or the EM spectrum. The electromagnetic spectrum refers to all of the types of energy that travel in the form of a wave. So this includes light, but it also includes things like radio waves and ultraviolet rays and X-rays and gamma rays and microwaves and all kinds of things that travel as a wave. In the middle of this series of waves, we see the visible light spectrum. And remember that red light has our longest wavelength, or our lowest energy, and our violet light of the Roy G. Biv is going to have the shortest wavelength and the highest energy. The way that you can remember that is that ultraviolet rays are the ones that cause sun damage, that cause damage to our skin, and it's because there's such high energy. But their term, ultraviolet, reminds you the high energy waves, the ones with the fastest wavelength or the highest frequency, those are going to be the ones that cause the damage. So violet rays and UV rays are right next to each other, even ultraviolet. So as we look at our electromagnetic spectrum, we can see that one side of visible light, so this is the visible light down here, one side is ionizing radiation. This is the kind that tends to be more damaging to our bodies, like UV, a tanning bed, or X-rays. That's why they put those lead vests over you when they do your X-rays. And on the other side of visible light, we have non-ionizing radiation, things like internet and radio signals, TV signals, and cell phone signals, all which are considered to be a safer type of wave. All of these waves, though, have the same speed in a vacuum. And we technically measure this in a vacuum. In a vacuum means in an area with no air to block the waves as they travel. As those waves get into Earth's atmosphere, of course, we do have some gases here, and so there is some impedance from those gases, but it's not so much that we have to change the value. So we describe the speed of light, the speed of all electromagnetic radiation, as being the constant 3.0 times 10 to the 8th meters per second. And I'm going to put this back here for me. You should have this value on your notes. Constants are things that you would never memorize. You would always look them up should you need them. So we have the value. This is the speed of light. And so we're going to be using that value a little bit later on when we get to our calculations. A few things about a wave. Again, these are things I'm repeating from the crash course that you guys watched, but I didn't have you take notes on the crash course, so it's important that you're writing these things down now. The length of corresponding points on adjacent waves is known as the wavelength. So when we look at a wave like these waves down here, we can see the measure of the wavelength, and we say that the wavelength is between corresponding points on adjacent waves. So adjacent just means next to each other. So we're looking at two waves that are next to each other, and we are looking for corresponding points. So in this case, we're measuring from crest to crest of waves that are next to each other in order to give us our wavelength. So this low frequency wave down here has a long wavelength, a longer distance between crests of the wave. And in this wave that is at a higher frequency, we see a shorter distance between the crests of the wave. So we say that this high frequency wave has a shorter wavelength, where a low frequency wave would have a longer wavelength. When we're talking about frequency, we are measuring how many waves pass in a given amount of time. So imagine that each of these black lines here represents the same time frame, maybe 1 second. If we were to look at the low frequency wave, in this 1 second of time, we would say that 1, 2, 3, 4 waves have passed. So the frequency of the low frequency wave would be 4 waves per second. 4 waves per second. Or the unit that we use for this is called a hertz. So we would call that 4 hertz is our low frequency wave. The higher frequency wave, if we were to count, we would say it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 waves per second, or 12 hertz. And remember that we just looked, this high frequency wave also has a shorter wavelength. Wavelength is represented by a lambda that looks like this. That's the symbol that represents the wavelength, and it's often measured in nanometers. A wave that has a low frequency, like this bottom wave, a wave that has a lower frequency is going to have a longer wavelength. Lower frequency, longer wavelength. Higher frequency, shorter wavelength. This relationship value can be represented by a mathematical equation. So what we see is that C equals frequency times wavelength. So we find that C equals frequency times wavelength. And what this is really telling us is that since all light moves at the same speed, if they have a shorter wavelength, a higher frequency will pass in a given amount of time. And if they have a longer wavelength, a lower frequency will pass in the same amount of time. So we have this mathematical relationship. Before we go on to the real math of this part, I want to take a moment with the equation to just make sure that we understand how it's all working. So this is the equation that we're talking about that equates frequency to wavelength and relates the speed of light to the frequency and the wavelength. So the shorter the wavelength, the higher the frequency is equal to 3.0 times 10 to the 8th meters per second. So now we get to apply this same equation to a question. So we're going to solve for the wavelength and color of a light that has a frequency of 6 times 10 to the 14 hertz. When we solve problems in this chapter, we are going to use the 5-step method. So if you recall, our first step is identifying our given. According to this question, what I am given is a frequency of 6 times 10 to the 14 hertz. My next step is the find. What I am trying to find in this problem is the wavelength and the color. We'll come back to this part at the end. For now, let's concentrate on finding the wavelength. After we do the given and find, we look for our U's. The equation that we have that relates frequency and wavelength is C equals frequency times wavelength. This is pretty easy right now because we only have one equation for this chapter. In a moment, we're going to have 2. So it's really important to identify your given and your find and make sure that both the given and the find are in the equation that you chose. We also know we're also going to use the constant of the value for C. C equals 3.0 times 10 to the 8th meters per second. So I have my given, my find, and my use. So it's time to go ahead and plug in. When I plug in, I am going to plug in C and frequency where they go. And of course, I'm solving for wavelength. So I get 3.0 times 10 to the 8th meters per second is equal to my frequency, 6 times 10 to the 4th, times my wavelength. The units of frequency are hertz, which are 1 over seconds. So now it's time to plug this in to my calculator. This is one of those things where we need to make sure that we are properly using our calculators. So when we plug this in, we want to hit 3 and then that EE button that we talked about in class, 3 EE 8. Just like that. Enter. Divided by 6 EE 14. 6 EE button 14 and hit enter. And we want to put that into scientific notation. So if you don't already have it in scientific notation, you want to do that. My answer that I get here is 5 times 10 to the negative 7. Wavelength equals 5 times 10 to the negative 7. And the unit here, because hertz cancels with seconds, the unit here is meters. So this is the official answer to the question of what is the wavelength of light with a frequency of 6 times 10 to the 14 hertz. We're going to solve for the color, but before I do that, I'm just going to review what happens right here with our units. So I have meters per second equal to hertz, which remember is a 1 over seconds. So when I divided by 1 over seconds, my seconds canceled, and I was left with the unit of meter for my answer. So that was how I knew the answer to that question. If I want to find the color, this is a little bit trickier. Colors are measured in nanometers. This number into nanometers. 5 times 10 to the negative 7 meters. Meters and nanometers. So all we have to do for that is we do negative 7 plus 9. And so we end up with 5 times 10 to the second nanometers, or 500 nanometers. That's how we're going to solve it. So we're going to solve it using dimensional analysis. So we get this answer of 500 nanometers. Now, how are you supposed to know how to do this? This is chapter 3, my friend. The sad news about chemistry is once we learn something, we're never allowed to forget it. We have to use it for all of the chapters. So we learned how to do dimensional analysis. We know how to convert meters to nanometers. So there we go, 500 nanometers. Now that we have found that we are looking at a wavelength of light that's 500 nanometers, we come over to our wavelength chart that's here. There are a variety of these available online, and I would provide you one if I wanted you to use it. You don't need to memorize this, but we would look at these wavelengths and we can see that 500 nanometers lands us right smack in the middle of green light. And so now we know that this frequency of light that we see is actually green in color. So if we happened to see this frequency of light, we would see it, our eyes would register it as a green color. So as we've already seen in our study of the atom, discovery after discovery after discovery moves us closer and closer to that final current version of the atom that we have right now. Final maybe, definitely current version that we have right now. And the next important person in this study is Planck. Max Planck is a man who described something called the photoelectric effect. And this really has to do with the fact that when you heat up a metal like iron, as you give it more and more heat, the iron then gives off different colors of light. First it glows red hot, and then finally it will glow yellow. And that has to do with the amount of energy that's coming in and then the amount of energy that's being given off. And this really kind of all encompasses into something called the photoelectric effect. This is the idea that if you gave enough energy to a metal, you might be able to convince that metal to eject electrons out of the metal and away. The question though is, how much energy does that take? It can't be easy to do. So how much energy would it take to cause those electrons to be moved? And what Planck sees is that high frequency radiation, higher frequency means a shorter wavelength, things like blue and violet and ultraviolet, could cause more of this ejection of the electrons, where lower frequency wavelengths, which means they have a longer wavelength, are going to have less energy in order to eject the electron, and they're not going to be able to do it. So what Planck sees is that the frequency of the light, high frequency blue, mid frequency green, or low frequency red, that those frequencies determine the amount of energy with which they hit the metal. And depending on the energy, you could now either see or not see the photoelectric effect. Are you able to eject those electrons? Depends on the energy of the electromagnetic radiation that's coming in. So there's Planck, and in addition to kind of helping to embody this theory, Planck also comes up with Planck's constant. So Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. This is known as Planck's constant, and we use this constant in our calculations of energy from frequency. So first let's put Planck's constant and the equation with its labels on the board. This is Planck's energy equation, where E is energy. Energy is measured in a unit called joules, represented by a capital J. F is frequency, and just like in the wavelength equation, frequency is measured in hertz. This is a good time to point out that your book actually uses a different variable for frequency. It is a different accepted variable. It looks like that. I prefer to use F. Some books, it just depends on which book you use, whether it's represented by an F or not. So I go ahead and use the F. I will also put this symbol on your tests and also in your homework. But if you personally want to use that symbol because you're using it out of the book, that's okay too. The last portion of Planck's equation is Planck's constant. And this one is 6.626 times 10 to the negative 34 joules times seconds. And that's joules times seconds because the joules will cancel out with these joules and the seconds will cancel out with these 1/seconds, and we'll end up with no extra units. So this equation that it's joules times seconds is quite important, and I would expect you to be able to include that in your work on a problem like this. Speaking of a problem like this, we're going to try one. As I mentioned before, for every kind of problem that we're doing in this chapter, we are going to be using the 5-step method. So the question is, what is the energy of green light with a frequency of 6 times 10 to the 14 hertz? So we start with given and find. Our given is 6 times 10 to the 14 hertz. This time though, we're being asked to find energy. If you look back, this is the same frequency that we used for our first problem, but that time we were trying to find wavelength. Now we're trying to find energy. This is one of the reasons why it's very important that you pay attention to both your given and your find when you're trying to decide which equation to use. For this equation, because we're trying to find energy, we're going to use E equals HF. So we can use Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Don't forget the unit. We're also going to be using that anytime we have a constant. They are always given, they're always available for us to use. So if you need to use it, go ahead and use it. Now it's time to plug in. H is 6.626 times 10 to the negative 34 joules times seconds. And of course, our frequency was given 6 times 10 to the 14 hertz. So we have our frequency and we have our Planck's constant, and we're going to use that to solve for energy. Before we solve for energy, let's remember that hertz, because it's a 1/seconds, cancels with seconds. And so the units of our energy are going to be joules. Now we're going to plug this into our calculators. Plug it in with me, guys. Make sure you know how to do this. 6.626. E, remember that EE button, negative 34. So I should have 6.626 times 10 to the negative 34. And now I'm going to do times 6, EE button again, to the 14th power. That gives me 3.98 times 10 to the negative 19 joules. 3.98 times 10 to the negative 19 joules. This is the energy of green light. By itself, maybe not a ton of energy, but just the same, we know that light brings energy with it, and this is the energy that we are measuring using Planck's constant. So we're able to measure the energy of a wavelength of light. We're able to just do math and figure out what that energy might be.